Dear ladies and gentlemen, in this presentation I will show you the highlights in BatteryDict in GeoDict 2021. With the new BatteryDict module, you can perform battery simulations faster and more accurately. But before I come to the actual presentation, I want to introduce myself. My name is Sven Linden and I am the Vice Head of the Software Development Team. I am responsible for the Lear solver that is able to perform flow, conduction and diffusion simulations in GeoDict. Since this year, you can use the solver technology also to perform battery simulations in BatteryDict. If you have any questions regarding these topics, please feel free to write me an email with your questions. My presentation is divided into 5 parts. First, I want to give a brief introduction about BatteryDict and about battery simulations. Then I will show the user interface improvements in BatteryDict that allow to set up battery simulations more easily. In the third and fourth part, I want to show the latest feature in the BEST microsolver, and I also want to show you the Lear as new battery solver in BatteryDict. The presentation is ended with a summary and an outlook about upcoming features. We start with a short introduction. With BatteryDict, you can design and analyze lithium-ion batteries. You can design full batteries with anode and cathode side, or you can design half-cell batteries with just a cathode or an anode side. After you have created a battery structure, you can perform charging or discharging simulations to get a detailed insight about its performance. In this slide, I want to show the basic principle of lithium-ion batteries. A lithium-ion battery consists of an anode and a cathode side. In the bottom left and right, you can see the complex microstructure of these electrodes. The electrodes consist of so-called active particles, a liquid electrolyte between the active particles, and carbon black and binder that glue active particles together. These active particles have a spherical or polyhedral shape and they host lithium atoms. At the beginning of the charging process, the cathode is full with lithium atoms and the anode is almost empty of lithium atoms. During this process, lithium atoms diffuse from the center of cathode active particles towards the interface of active material and electrolyte, the so-called Butler-Former interface. The lithium atoms lose an electron and travel through the electrolyte and the separator to the anode active particles. The electrons travel through the carbon black and binder to the current collector and then through the charging device to the other side. On the anode side, lithium atoms meet other electrons and they migrate into anode active particles. After you have performed the charging simulation, you get different kinds of results. The cell potential curve, which shows the cell potential difference between the two current collectors at different state of charge. The cell potential curve grows with increasing state of charge. There are two curves. The equilibrium curve, which shows the cell potential when no electrical current is flowing, and the cell potential curve while loading. This curve is typically higher than the cell potential curve in equilibrium. In the beginning, the lithium concentration is high at the cathode side and low at the anode side. During the loading process, the lithium concentration gets lower on the cathode side and grows at the anode side. A concentration gradient may also occur depending on the diffusivity of the active particles. In the second part, I will show you the latest improvements in the user interface of BatteryDict. The graphical user interface of BatteryDict got a lot of improvements. In GeoDict 2020, the solver choice was outside in the module interface, and the design step was integrated in the charge battery command. In GeoDict 21, the solver choice is inside the charge battery command, and we now have a workflow of designing, analyzing and charging of batteries. The workflow is now shown briefly. First, you can design batteries with a battery designer where you can design full or half-cell batteries. Here you just need to provide the microstructure of an anode and the cathode side, and they are layered together with a separator and current collectors on both sides automatically. With the Analyze Battery command, you can check the validity, connectivity, and layered solid volume content of a generated battery microstructure. First, the validity of a battery is checked. The current collectors and separator must be planar, such that the simulations can be performed in X direction. If this is not the case, then you get an error message as shown here in this example. Then, the connectivity of active particles and the electrolyte is checked. Active particles should be connected to the current collector through the binder and other active particles. And they should also have connection to the electrolyte. The electrolyte on the anode side should be connected through the separator to the electrolyte on the cathode side. The volume fraction of unconnected materials or electrolyte is then shown in the report of the Analyze Battery command. At the end, you can look at the layered porosity or electrolyte content over the X direction. Now we come to the Charge Battery command. Here we reduced the complexity and made it easier to assign material properties to the different material phases. It is now also more clear how to enter simulation and solver parameters. In Geodic 2020, the Charge Battery command consists of 6 different tabs. These are now reduced to 4 tabs, where anode, cathode and electrolyte properties can be entered in the Constituent Materials tab, like in the other DICT modules in Geodict. The Solver Options tab is split into 2 tabs, namely the Experiment and the Solver tab. In the Constituent Materials tab, you can assign a role of each material ID. For example, if it is electrolyte, or if it's a separator, or if it's an active material. And for each of these roles, you can assign material properties. For example, if you click Edit on one of the active materials, a new dialog shows up with specific active material properties. Here you can, for example, see the open circuit potential for different state of charges, or the diffusivity constant, or the Butler-Volmer constant. In the Experiment tab, you can enter charge or discharge specific parameters. For example, the charge rate or which state of charges you want to simulate. In the third section of this presentation, 2 new features of the BEST microsolver are shown, namely the support of Power's carbon black and binder domain and the support of cutoff potentials. One of the new highlights in the BEST microsolver is the support of Power's carbon black and binder domain. But why do we actually need to model the carbon black and binder as Powers? Battery researchers want to design batteries with higher capacity. And this can be done by increasing the packing density of the active particles and thus to decrease the amount of electrolyte. The microporosity of the carbon black and binder becomes significant at some point, but its pores cannot be resolved well enough. If you do not consider the carbon black and binder as porous, then you can get a significant amount of closed porosity, and this closed porosity cannot contribute to the battery performance. But we have a solution for this. The carbon black and binder is modeled as porous in a multiscale approach, similar to the Brinkmann term in the Stokes-Brinkmann equations. The Powers carbon black and binder in the BEST microsolver is implemented such that it has 2 potential variables in porous voxels, one for electrolyte and one for the carbon black and binder. On the right side, the input dialogs for this feature are shown. The first parameter needed to model Powers carbon black and binder is the porosity, that means the electrolyte content. Then the solver needs to know the effective electrical conductivity, the ionic conductivity, and the ionic diffusivity. You can enter these parameters directly with the effective values input mode, or you can enter the tortuosities of the carbon black and binder content and the pore space content when effective values are computed automatically. Here is an example where a charging simulation from 20 to 70% was performed on a full battery structure with 509 × 200 × 200 voxels. The cell potential curve is shown on the left bottom side with and without the new feature. The equilibrium curve is shown with black dashed lines. The cell potential curve without post carbon black and binder is shown in red, and the blue line is the cell potential curve with post carbon black and binder. One can clearly see that it makes a huge difference when the porous nature is considered in charging simulations. The electrolyte has a better connectivity, and this leads to a lower cell potential. In this case, the cell potential with post carbon black and binder is right in the center of the other two curves. Fortunately, the run times for both simulations with 39 hours is equal, and the memory consumption is increased by just 5%. Another interesting new feature is the cutoff potential for charging simulations. Depending on the charge rate, the thickness of a battery, the size of the active particles, or their diffusivity, the cell potential may diverge to very high values, and they cannot be maintained by the power supply to get a constant charge rate. This divergent behavior comes from the effect that the concentration at the Butler-Volmer interface is very small on the cathode side and very high on the anode side. The concentration in the active particles diffuse too slow to or from the center of the active particles, and this leads to a high potential difference between electrolyte and active particles. In this case, it is common to charge the battery further, but instead of using a constant charge rate, a constant potential is used until the battery is full. This can now also be modeled in BatteryDict with the BEST microsolver. An example is shown at the bottom left, where the cell potential is cut off at 4.1 volt. And here it happens at about 50% of state of charge. In the fourth part of the presentation, I would like to introduce the Lear as new battery solver in GeoDict, also called BatteryLear. The BatteryLear solver was started by Fabian Wiebel and myself beginning of this year within the Solve project. The goal is to replace the BEST micro-FFT solver, which is no longer developed anymore and which is also not part of BatteryDict in GeoDict 21. The solver should have comparable or faster runtimes using less memory than the BEST microsolver. The equations that govern the transport of lithium and electrical charge are highly nonlinear, and the Butler-Volmer interface leads to extremely high conductivity contrast. Here, different methods are used to overcome these challenges. For example, the Newton method to deal with nonlinear behavior, or the BiCG step solver method for the high conductivity contrast. The BatteryLear solver already supports many different features. You can do charging or discharging simulations. It also supports multiple active materials per electrode. You can also model inclusions as material phase, where we have no lithium and no electrical flux. And you can simulate half-cell or full-cell batteries. In the future, we also want to support post carbon black and binder like the BEST microsolver. In addition, the BatteryLear will be able to simulate anisotropic diffusivities in the active particles. And the multigrid acceleration will speed up the simulations even more. The BatteryLear solver can be chosen in the BatteryDict Solver tab. The solver parameters are similar compared to other simulation modules. Here, BEST Micro and BatteryLear share same parallelization and time step settings. During the execution of the charge battery command, the Lear solver is started once per time step. Now we want to compare the results, runtime and memory requirements of BatteryLear and BEST microsolver. We use 3 different benchmark cases: a 1D structure, a 2D structure and a large 3D structure. In our first example, a 1D battery structure is used as shown in the bottom. The anode active material is shown in yellow and the cathode active material is shown in brown. Conductivities are equal for current collectors and the carbon black and binder. Here, the anode active material has a much higher conductivity than the cathode active material. The cathode active material is less diffusive than the anode active material, and the diffusivity of the electrolyte is much higher. We use a charge rate of 10 C and we charge from 20 to 70%. The focus in this example is about the result comparison rather than runtime or memory. The computed cell potential curves of BatteryLear and BestMicro are equal. The cell potential curves, while loading deviates a lot from the equilibrium curve, and its shape is different at high state of charge. The computed potentials and concentration values are also equal for the BatteryLear and BestMicro solver. This 1D example makes it easy to see the effects of different diffusivity values. The low diffusivity in the cathode material leads to a strong concentration gradient towards the electrolyte interface from 20 to 50% state of charge. The second example is a 2D structure made with the EDIT-U module in Geodict. It consists of 2 active particles per electrode and carbon black and binder that connects them to the current collectors at the left and right boundary. The conductivities and diffusivities are similar to the first example, but the charge rate with 3C is a little bit smaller. Again, the computed cell potentials are almost same, and here we can compare runtime and memory requirements. The runtimes are similar, but BestMicro needs 4 times as much memory than the BatteryLear. The streamlines of electrical current start at the current collector and they travel through the carbon black and binder, active particles, electrolyte and separator towards the active particles on the other side, then over the carbon black and binder to the other current collector. The flux of lithium concentration starts at the center of active particles, and then lithium travels through the electrolyte and separator towards the center of the active particles on the other side. In our last benchmark case, we used a large 3D battery structure and we loaded with 3C from 20 to 70%. The conductivities and diffusivities are slightly different compared to the other examples. Here, the structure has a size of 409 × 400 × 400 voxels. Also in this example, the computed cell potentials are almost same, but now the BatteryLear can benefit from a much better parallelization. Here, the BatteryLear needs just 22 hours compared to the 72 hours of the BestMicro solver. The BatteryLear needs just a fraction of the memory that the BestMicro solver needs. Just 8 GB compared to the 254 GB. The new solver allows to perform battery simulations on much larger structures than before. And with larger structures, you can simulate batteries even more accurately on a modern workstation. This is now an example where the battery structure is so large that we cannot compute it with the BestMicro solver on our compute servers. The battery structure has 509 × 1000 × 850 voxels, or more than 400 million voxels. The BatteryLear solver needs around 4 days of computation for a charging simulation from 20 to 50%. And it just needs 41 GB of RAM. So you can simulate such a large battery on a small workstation easily. We are approaching the end of the presentation. Now I would like to sum up the presentation. The user interface of BatteryDict is improved a lot, with a new workflow of design, analyze and charge batteries. The BestMicro solver is now able to consider Power's carbon black and binder in batteries. I have also introduced the BatteryLear solver as a new solver generation in BatteryDict. It needs up to 30 times less memory compared to the BestMicro solver. It has similar runtimes for small and much less runtimes for large structures. And in the future, the BatteryLear will also support Power's carbon black and binder and anisotropic diffusivities in active particles. In the last slide, I want to acknowledge the SOLVE project and the Structure E project for funding the development of a battery Lear solver and for the anisotropic diffusion feature in DiffuDict and BatteryDict. Now, thank you for listening to this presentation.